In this lesson, we're looking at sketching and modeling quartic polynomials. Now, there is more to this lesson, but I want to keep it nice and simple, so I'm going to say we're going to focus on the translation template. So in this case, we're basically just looking at that y is equal to a f of x minus h plus k, and because specifically we're looking at quartics, it means we're looking at a polynomial to the power of 4, so we're looking at y is equal to a x minus h to the power of 4 plus k. All right, so that's our goal. That's what we're looking at. We're going to examine this particular shape. All right, so knowing now that our focus is on the template, y is equal to ax minus h to the power of 4 plus k, knowing that a is vertical dilation and that it also determines whether it's upright or inverted. We know that h is horizontal translation and that k is vertical translation. We'll quickly go into Desmos and have a little bit of a look so you can see how this compares to other types of functions. Okay, so in Desmos, we'll start by looking at y is equal to x squared, and we'll compare that to y is equal to x to the power of 4. So you can see it's got a similar shape, but the curve is more pronounced and it increases at a greater rate. So you can see these two curves, while they have a similar shape, are slightly different. So it looks flatter on the bottom. So we can tell the difference between a parabola and a quartic by the rate of change. And if I went one further and I went y is equal to x to the power of 6, we could see it's even more pronounced. So I'll get rid of that one. If we look at a cubic, we can see it's got that different shape. So we're going from even shape to an odd shape with our cubic. Now, again, if we look at x to the power of 5, it's going to be a similar shape. Now, the good news is you don't have to know about power of 5. You don't have to know about power of 6. Our lesson is on a quartic, which is y is equal to x to the power of 4. All right, so we can see the difference between the quadratic. Let's get rid of that and let's change our setup so we can examine what the parameters do. So y is equal to a x minus h to the power of 4 plus k. So when I add this in, we've got our sliders. Let's change h to 0 and k to 0. So we know that our vertical translation and horizontal translation is 0. And let's examine what a does. So a we know is vertical dilation. When it's big, it stretches it out. So it looks like it's squashing it in the horizontal, but what it's really doing is it's stretching it vertically. Now we also know that when that's between 1 and 0, it compresses it vertically, so it's squashing it down. And when it becomes negative, we know the opposite happens. It's inverted, so it looks like it's flipped in whatever that k value axis is. So now because k is 0, it's flipped in the x-axis. If k was 1, it would be flipped at the line y equals 1. All right, so we can see that. It's nice and easy. That's what our a value does. It shouldn't be too difficult, but we know that we can change the h value. It shifts it left to right. When h is positive, it moves it right. When h is negative, it moves it left. And with k, when it's positive, it moves up, and when it's negative, it moves down. Okay, so that should make sense. We can now write these things down. We can see our shape. So if we look at our shape, we know it's that more pronounced curve. It looks a little bit flatter on the bottom, a horrible representation of what it should be. That's what our quartic looks like. So before we go into an example, we want to point out what the critical features are. So obviously critical features with a quartic in this form, that translation form, should be the first one. It'll have a turning point, which will be hk. So it's very similar to the quadratic. The second thing is that we can look at a y-intercept. And the y-intercept is when x is equal to 0. And x-intercepts where it could have no x-intercepts, 1 or 2 x-intercepts, is when y is equal to 0. So there could be 0, 1, or 2 of these. It will also have an axis of symmetry, but there's no need for you to deal with this. So axis of symmetry is x is equal to h. All right. So this point here obviously is very important, hk. And then, like always, we calculate the x-intercepts and the y-intercept. So now we'll look at an example, and we'll look at sketching using the template. We're trying to sketch the graph of y is equal to x take 2 to the power of 4 take 1. Now we know straight away that a is equal to 1 because that coefficient in front of the bracket isn't there, so there's an implied 1. H is equal to 2. Be very careful. Remember that this is x take h to the power of 4. So negative 2 is equal to negative h, and therefore h is 2. So we always invert that value. And then finally, k is equal to negative 1. So it's shifted 1 down. Straight away, we can state our turning point, and our turning point is hk, which will be 2, negative 1. So we already know where it's turning. And now we can work out our x-intercept or x-intercepts by looking at y equals 0 and our y-intercept at x equals 0. The easier of these two is the y-intercept, so we'll do that first. So y is equal to 0 take 2 to the power of 4 take 1. Negative 2 to the power of 4 is 16, so we've got 16 take 1. We end up with 15. That means our y-intercept is x is 0, y is 15. There we go, we've now got 2 critical points. When we let y equal 0, so now we'll find the x-intercepts. We've got 0 is equal to x take 2 to the power of 4 take 1. This whole process is about isolating x. So first we can add 1. We add 1 and we get 1 is equal to x take 2 to the power of 4. We can take the quartic root. When we take an even root, it's always going to be plus minus. So quartic root of 1 plus minus is equal to x take 2. The only answer to that is 1, obviously. So we end up with plus or minus 1 is equal to x take 2. And we can isolate x, so we get 2 plus or minus 1. So now we've got our two answers. X is equal to 2 plus 1, which is 3. And x is equal to 2 take 1, which is 1. So our two critical points are 3, 0 and 1, 0. So now we've got everything we need to do a nice sketch. So I set up my Cartesian plane as a sketch, so it doesn't have to be perfect. And we've got 2, negative 1. So 2, negative 1. We've got 1, 0. So 1 and 3, 0. And right up here, we will have 15. So if we follow that down, remember in our shape, remember it's a little bit squarish on the edge. And unfortunately, I'm never great at drawing these on the computer screen. I'm sure you'll be better than me. We've got our sketch right there. Now if we want to, we can add in our axis of symmetry. We don't have to have it. And we can say that's x is equal to 2. All right, so there's our nice, easy sketch, easy to follow. The process is really similar to what we've learned with our parabolas and our cubics and hyperbolas. Just a matter of critical points and then sketching out using the shape that we know. Now, the other skill is modeling. Now, the big thing with modeling, as we saw in the previous lesson, is that it all comes down to making sure you use the right template. We know it's a quartic. It's got a turning point at 3, 1, so we know that gives us hk. And we've got another point, so that allows us to find the a value. So that's our goal. The process is the same. Our starting template, because it's a quartic, is y is equal to a x minus h to the power of 4 plus k. We know that h is equal to 3 and k is equal to 1. That's given to us with that turning point. So we can fill those in, and the only parameter that is unknown is the a value. We can use this information, x is equal to 0 when y is equal to negative 20, to determine that a value. So if we substitute them in, we've got negative 20 is equal to a, x is 0, so x take 3 to the power of 4 plus 1, negative 20. Now, negative 3 to the power of 4 is 81, so we've got 81a plus 1. And now we can just isolate a, so subtract 1, we've got negative 21. Divide by 81, and we end up with a is negative 21 on 81. Beautiful, we've got our a value. So our final answer is just going to be stating the model that fits the scenario, and that is y is equal to negative 21 on 81, x take 3 to the power of 4 plus 1. Okay, so if we sketch this, this would fit our conditions where we've got that turning point at 3, 1, and it passes through that point, 0, negative 20. Obviously, that would be an inverted one, so it would be upside down. And I determine that by looking at that a value. We've got a negative a value, so it's an inverted quartic. Okay, so that's our skills with quartics. We will look at more complex quartic polynomials later when we are factorizing and sketching factorized polynomials. Okay, thank you very much.